Welcome to the mysterious realm of paradoxes and thought experiments, where reality itself seems to unravel at the seams. I'm Dr. Alexandra Mercer, and today we're venturing into the twilight zone of human reasoning. What happens when logical thinking leads us to impossible conclusions, when our most fundamental assumptions about reality collapse under their own weight? That's precisely what we'll explore in the next 20 minutes. Paradoxes and thought experiments have been the secret weapons of philosophers and scientists for centuries. They're intellectual puzzles that challenge our deepest intuitions about the universe. A paradox occurs when seemingly sound reasoning leads to contradictory or absurd conclusions. A thought experiment, meanwhile, is a hypothetical scenario used to explore the consequences of theories and principles. Together, they've catalyzed some of the most profound scientific revolutions in history. Einstein's relativistic theories, quantum mechanics, and even modern computing all emerged from confrontations with paradoxes. Let's begin our odyssey with one of the oldest paradoxes in Western philosophy, the ship of Theseus. Imagine an ancient vessel, preserved for centuries. Over time, its wooden planks decay and are replaced one by one. Eventually, every single component has been swapped out. The question emerges, haunting and inescapable: is it still the same ship? And if not, at what precise moment did it cease to be the original? But wait, there's a twist. What if someone collected all the discarded original planks and reconstructed a second ship? Which one, if either, is the true ship of Theseus? This ancient riddle resonates in startling ways with modern science. In biology, our bodies replace nearly all their cells over a lifetime. In neuroscience, memories are constantly reconstructed. Even in quantum physics, particles exist in states of superposition until observed. The ship of Theseus forces us to confront the elusive nature of identity itself. Are you the same person you were a decade ago, when almost every molecule in your body has been replaced? Next, we encounter the bewitching Sorites paradox, also known as the Heap paradox. It begins deceptively simply. Imagine a heap of sand. If I remove just one grain, it remains a heap. I remove another grain, and surely it's still a heap. But if I continue this process, grain by grain, eventually I'll be left with just one grain. That's clearly not a heap. Yet there's no clear boundary, no precise moment when the heap transforms into a non-heap. This paradox exposes the vagueness lurking in many of our concepts. When does a fertilized egg become a human? At what point does removing trees from a forest make it no longer a forest? The boundaries blur before our very eyes. Perhaps most maddening is the self-devouring liar paradox. Consider this statement: this sentence is false. If it's true, then it must be false. But if it's false, then it must be true. The statement seems to chase its own tail eternally, never resolving into stable truth or falsehood. This isn't merely linguistic trickery. The liar paradox struck at the heart of mathematical logic when Kurt Gödel used similar self-reference to prove his incompleteness theorems, showing that no consistent mathematical system can prove all true statements about itself. The foundations of mathematics trembled. Now we venture into the quantum realm with Schrödinger's cat, perhaps the most famous thought experiment in modern physics. In 1935, Erwin Schrödinger proposed a scenario to illustrate the apparent absurdity of quantum superposition. A cat is sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter detects it and triggers the release of poison, killing the cat. According to quantum mechanics, until we open the box, the atom exists in a superposition of decayed and undecayed states. The unsettling conclusion? The cat must exist in a superposition of alive and dead states simultaneously until observation collapses the wave function. This thought experiment wasn't just provocative, it exposed profound questions about quantum reality. Does consciousness play a role in collapsing quantum states? Where exactly is the boundary between quantum and classical physics? While Schrödinger intended to highlight quantum theory's apparent absurdity, his feline phantom has become emblematic of quantum mechanics itself, a realm where particles exist as probabilities until observed, where reality itself seems indeterminate and observer-dependent. Let's meet another spectral entity, Maxwell's demon. In 1867, James Clerk Maxwell imagined a tiny being guarding a door between two gas chambers. The demon selectively allows only fast-moving molecules to pass in one direction and slow ones in the other. Over time, one chamber becomes hotter than the other, apparently violating the second law of thermodynamics, which states that entropy always increases in a closed system. This demon haunted physics for decades. The resolution? Information itself has a thermodynamic cost. The demon's knowledge acquisition and decision-making generate entropy that balances the books, preserving the second law's integrity. Einstein's elevator thought experiment transported us to the cusp of revolutionary insight. Einstein imagined being inside a closed elevator, unable to see outside. If the elevator accelerates upward, you feel pressed to the floor, indistinguishable from gravity's pull. This led to his equivalence principle. The effects of acceleration are indistinguishable from gravitational effects. This realization was the cornerstone of general relativity, which reconceived gravity not as a force, but as curved spacetime. With a single thought experiment, Einstein transformed our understanding of the cosmos itself. Time travel paradoxes evoke particular wonder and dread. The grandfather paradox asks, what if you traveled back in time and prevented your grandfather from meeting your grandmother? You would never be born. But then, who traveled back in time? The paradox creates an impossible loop, a causal contradiction that seems to forbid time travel entirely. Physicists have proposed resolutions, parallel timelines, self-consistent loops, or quantum branching. But the paradox continues to haunt our understanding of time's true nature. Related but distinct is the bootstrap paradox, or causal loop. Imagine a historian who discovers an antique book of Shakespeare's complete works. Traveling back in time, the historian gives the book to Shakespeare himself, who publishes it as his own. But here's the question that fractures causality. Who originally wrote the plays? The information exists in a loop with no clear origin point. It bootstraps itself into existence. These temporal paradoxes may seem purely theoretical, but they probe the fundamental nature of causality and time's arrow, concepts central to physics. Decision theory gives us Newcomb's paradox, a mind-bending scenario involving an infallible predictor. She offers you two boxes, one transparent with $1,000 visible inside, another opaque that contains either $1 million or nothing. The predictor has already placed $1 million in the opaque box if and only if she predicted you would take only that box. If she predicted you'd take both boxes, she left the opaque box empty. The paradox emerges. Rationally, you should take both boxes since the predictor has already decided. Yet the predictor is infallible, so taking only the opaque box leads to greater gain. Rational decision-making seems to undermine itself. The prisoner's dilemma illuminates the tension between individual and collective rationality. Two suspects are interrogated separately. Each can either remain silent or betray the other. If both remain silent, they receive minor sentences. If both betray each other, they receive moderate sentences. If one betrays while the other remains silent, the betrayer goes free while the silent prisoner receives a harsh sentence. Rational self-interest suggests each should betray, yet this leads to a worse outcome for both than mutual silence. This paradox pervades social sciences, explaining everything from arms races to climate change in action. Modern science continues to generate new paradoxes. In computing, the halting problem proves that no algorithm can determine whether arbitrary programs will ever finish running. In artificial intelligence, Moravec's paradox reveals that abstract reasoning is computationally simpler than basic sensory-motor skills that even insects master. These paradoxes aren't mere intellectual curiosities, they're doorways to discovery. Quantum computing emerged from grappling with quantum paradoxes. Behavioral economics was born from decision theory paradoxes. I encourage you to develop your own thought experiments. They're not just the domain of Einstein and Schrödinger, they're tools anyone can use to explore the boundaries of understanding. When you find yourself at the edge of a paradox, you're standing at the frontier of human knowledge. That vertiginous feeling, the sense that reality itself is slipping through your fingers, that's the sensation of your mind expanding. In our next lecture, we'll explore cutting-edge scientific theories that push the boundaries of our understanding even further. Until then, remember that in the most baffling paradoxes often lie the most profound insights.